So we're continuing our introduction to vector-valued functions. Vector-valued functions are the mathematical tool to use when you're tracking a moving object in space. If r is a vector-valued function, then we could define the unit tangent vector, the unit normal vector, the curvature kappa, and the function s. All of these r, t, n, kappa, and s are functions of t. You think of t as time, so at different times t, I'm at a different position on the curve, I have a different unit tangent vector, normal vector, the curvature might vary, and this function s gives me the distance traveled by my curve from 0 up until t. So all of these are functions of little t. I just chose not to write them in because it'd make the formulas a lot longer. In this video, we're going to define 3 words from physics. You've seen them before, but let's write them in context with our vector-valued functions. So the first is speed. Speed is none other than the magnitude of the derivative of your vector-valued function. So that's speed. It's a function of t. At different times, you have different speeds. Speed is really the derivative of this function s I've defined over here. So I could write it as s prime. Simply, the fundamental theorem of calculus tells us derivatives and integrals undo each other, so the derivative of both sides would be the speed. Velocity is the name given to this derivative of the vector-valued function. Velocity is a vector where speed is not a vector. Velocity can be written in terms of the unit tangent vector. So if you take this equation for the unit tangent vector, multiply both sides by the speed, we find velocity is s prime times t. Meaning velocity is in the direction of the unit tangent vector and it has magnitude speed. The last new term I'd like to define is acceleration. Acceleration is defined to be the second derivative of your vector-valued function. So you've seen these 3 terms before, actually, if you've taken any course in physics, and you probably realize how fundamental understanding speed, velocity, and acceleration really are when tracking moving objects. I'd like to start this video by writing acceleration in terms of t, n, kappa, and this s. So let's try. We see that the acceleration, r double prime, is the derivative of velocity. Velocity I can rewrite as s prime times t. And then I could differentiate using the product rule. So this is equal to s double prime t plus s prime t prime. Now, t prime can be written in terms of the unit normal vector. Changing t prime into the unit normal vector, I get s double prime t plus s prime, and then to take this and write it as the unit normal vector, I think about multiplying both sides of this equation by the magnitude of t prime. So I get the magnitude of t prime times the unit normal vector n. I could take the magnitude of the derivative of the unit tangent vector and write that in terms of the curvature kappa. So this is s double prime t. When I take this and write it in terms of kappa, I get an extra factor of the speed, so I'll get s prime squared kappa n. So this is my desired expression for the acceleration of my vector valued function. This is somewhat interesting. It says that the acceleration, even if I'm in R3, so three-dimensional curve, the acceleration is always a combination of the t and the n vectors. So in this expression, t and n are vectors, and the terms in front of t and n are not vectors. They're scalar functions. So the acceleration is always in the plane described by the t and the n vectors. Furthermore, I could tell you exactly the components in the t and the n direction. Here, let me draw you a little picture. So I'm going to draw this in R2 just because it's easier to draw in R2. And then in the next video, I will show you three-dimensional images generated by a computer to show you exactly that the acceleration is in the plane generated by t and n and never has any component in the direction of the unit binormal vector. But for now, let's draw an R2. So maybe I've got, my curve described by my vector valued function here, r. I could have a point on the curve. So here's a point on the curve. The unit tangent vector is tangent to my curve and length 1. So let's say that's my unit tangent vector. My unit normal vector is perpendicular to my unit tangent vector and has length 1. The acceleration is a vector maybe like this. So let's say that is my acceleration, r double prime. If I drop a perpendicular towards the vector t, then this length, the length of this base of the triangle would be s double prime. So I kind of wrote over my t symbol there. There's my unit tangent vector, t. The length of the acceleration in the t component is s double prime, the derivative of the speed. And the other side of the triangle, this side of the triangle, is the amount of acceleration in the n component. So if I drop, maybe a perpendicular this way to see more clearly, the length of the component in the n direction is the speed squared times kappa. Okay, let's do an example with a calculation. So here's an example. Let's say that my vector valued function r is the vector valued function t sine t sine t. Let's write the acceleration of this vector valued function in terms of the unit tangent and the unit normal vectors. So the derivative, the velocity, is 1 cosine t cosine t. The acceleration, the second derivative, is 0 negative sine t negative sine t. So I have the acceleration. I'd like to write the acceleration in this form. So I'm going to find the speed, s prime. I'm going to find the derivative of the speed, and I'm going to find the curvature. So from this second line, I guess we have the speed, s prime, is the magnitude of the velocity. So this would be the square root of 1 plus 2 cosine squared t. I can take the derivative of that and get s double prime. So the derivative, this, if you like, can be written as 1 plus 2 cosine squared t to the 1/2 power. So the derivative would be 1/2, 1 plus 2 cosine squared t to the negative 1/2 power, and then by the chain rule, I have to multiply by an extra factor of 4 cosine t sine t. So there is my derivative of the speed. So I have the derivative of the speed, I have the speed squared. Lastly, I need the curvature kappa. So I could find the magnitude. I'll use this cross product idea to find the curvature kappa. So the magnitude of r prime cross r double prime, let's see here, is the magnitude of the following vectors. So I already have these two vectors lined up, ready to take the cross product. Crossing off the first row and column, I get 0 as my first component. My second component would be sine t. Remember, I have an extra negative sign in the middle component of the cross product. And my last would be negative sine t. So the magnitude of the cross product is the magnitude of this vector, which I believe, if you do the calculation, would be the square root of 2 times the absolute value of sine t. Okay, so, that's the magnitude of this cross product. And then the curvature kappa is this magnitude divided by the speed cubed. So 1 plus 2 cosine squared t to the 3/2 power. All right, so what do we have? Therefore, the acceleration, r double prime, is this term. So let me write it as 2 cosine t sine t divided by the square root of 1 plus 2 cosine squared t times the unit tangent vector plus the speed squared, so 1 plus 2 cosine squared t, times the curvature, which is the square root of 2 absolute value sine t, divided by 1 plus 2 cosine squared t to the 3/2 power times n. So I was able to express the acceleration as a combination of the unit tangent and the unit normal vectors without actually having to compute t or n. All right, join us in our next video where I show you 3D images of what's going on with acceleration. I'll see you there.